Hello everybody. Today we're going to look at indefinite integrals. That is our topic of discussion. So, indefinite integrals, what's going on? Well, first of all, you got to get used to the new symbols. So we're going to go straight into examples to work out what's going on. So I would love to find the indefinite integral of 2x dx. Whoa, a lot of new things going on here. Well, really, if you break it down, it's not that bad. I kind of look at these as bookends to the indefinite integral. This is what we call the integral sign. And please look for better integral signs than I'm showing you. Just Google it. That looks like an S. I know. It's not an S. This is called the variable of integration. So, indefinite integrals, or anti-differentiation, really we're working on the opposite of the derivative. So we've been working a lot on the derivative if you've been following my videos. We've been doing a lot with the derivatives. So this is our chance of asking the following question. This is the derivative of some function. What function would have that as a derivative? That's really what it is we're going to go backwards now. So this is the derivative of some function. Where did it come from? Well, here it is, my friends. Think about this. What function would that have that as a derivative? We can make an educated guess. We could think, because I understand derivatives, since that's got an exponent of 1, when you take the derivative, it's power down, subtract 1, right? So if I'm going to go backwards, instead of subtracting 1, I should bring the power up 1. So if I bring the power up 1, I'm now at x squared. And just for checks, just for giggles, the derivative of x squared is, you betcha, 2x. So this is the first chance for us to find the indefinite integral, the antiderivative. There it is. It's x squared. So the answer to this, it would be equal to x squared. But that's not the complete story, because what if I said it was x squared plus 60? Well, let's check the derivative of this. The derivative of x squared is 2x. That matches. The derivative of 60 is 0, so it's gone. What if I said it was x squared plus 601? The derivative of x squared is 2x. The derivative of 601 is 0. What if it was x squared minus 6013? The derivative of this is 2x. The derivative of this is 0. I hope you're getting the point. There could be a constant that upon taking the derivative vanishes. So when you anti-differentiate, when you go backwards and you integrate, you have to automatically put this constant, and I'm going to use the constant k. I don't want to use c because c usually stands for cost in business equations. So it's x squared plus some constant. What constant? We won't know yet. When we do some applications, please stay tuned for that. You'll see I can find this constant. I just need to know a particular point on the original curve to do it. Right now, I know this is the antiderivative of that. How do I know that? Because I'm really good at derivatives. The derivative of x squared is 2x. The derivative of constant, I don't care what number it is, 60, 601, 6013, the derivative of all those numbers is 0. So please make a mental note of that for my videos. K is a constant. K is your favorite number. Can we find it? Yes. Please stay tuned for my applications to integrals, and you'll see many examples in which I'll find it. So the game today is, if I write down an integral, can we figure out where it came from? So the integral of 8 dx. So again, to me it's a game. This is y prime. This is the derivative. Where did it come from? What original function has that as its derivative? And because we know the constant rule probably really well, the derivative of 8x is 8. So it begs the question, the antiderivative of 8 is 8x. What we're doing right now is working on the inverse function, right? The derivative goes this direction. The derivative of 8x is 8. We are now working backwards. The antiderivative, kind of like squaring, square rooting, adding, subtracting. Now, derivative, done that all year long. Let's go backwards now. The antiderivative of 8 is 8x, of course, plus some constant k. What's the constant? Again, not worried about it in this video. Just want to get there. Plus 8, the derivative of 8 is 0. Plus 13, the derivative of 13 is 0. I need to make sure the derivative of 8x is right there and matches. Before I get too crazy, I do want to look at a silly example that ties students up. The integral of 10 dz. It looks like a very simple antiderivative to do. Check it out. See if you get it right. Why am I pausing? Well, because sometimes people go too fast and they get hurt. What we have here is, I want the antiderivative of 10. Notice I sneakily changed the variable of integration. This is the variable we're using in the problem, which means it's not 10x. No. No soup for you. It's 10z, because that's the variable of integration. That's the variable I'm looking for. The derivative of 10z is 10. That's the variable I'm looking for, so I have to use the variable z. And of course, yes, I need plus k. Please be careful of that. This is the variable of integration. When you integrate back, that should be the variable utilized. This is the variable of integration. When you integrate back, that should be the variable you utilize. That's very important when you're doing these Calc 1 integrals. All right, let's start to work now. Now that you got the kind of base level, first of all, let's just jump right into it. There are two formulas that we utilize over and over. That is the integral of most powers, x to the n, dx, will be 1 over n plus 1, x to the n plus 1 plus k. This is our shining star. This is our numero uno formula. Now, it does not work in one case. That is, if n is -1, we are in trouble. We'll look at other videos to see that. We will not deal with powers where x is -1 in this video. That'll be when we look at log videos. Hint, hint, wink, wink. When you look at logarithms, you might see a power of -1. So x to the -1, no go here. Any other power for n, I got your back. Any other power for n, this is the antiderivative. How do I know? Because guys, I can take the derivative fast. How do you take the derivative? Bring the power down. 1 over n plus 1 times n plus 1, they multiply it out. They turn to 1. This multiplied down, these cancel out and get 1. Subtract 1 from n plus 1, you get n. Derivative of k is again 0. So this is a perfectly true statement. Also, I don't have kind of room to write it, but if I'm looking at the integral of a plus, I can integrate each piece. If I'm looking at the integral of a minus of two functions, I can integrate each piece. I'm going to utilize that in my next example. That is, I'm going to have 3x to the 4th plus 18x minus 10 dx. This type of integral. Well, the game, this is the derivative of some function. Where did it come from? That's really what this is. This is the derivative of some function. Where did it come from? Can we undo the derivative to get back to the original function? This is the marginal cost. I want to get back to cost. This is the marginal profit. I want to get back to profit. We now have the rate. I want to get back to the original function. How do we do it? Okay. So first of all, at a plus and a minus, you may break this into smaller little problems. And if there's a constant in your problem, you may break that out in front, as you'll see what I'm doing once I have written it down. So I'm working on 2 rules right now, or 3 rules actually. If you see a plus, you may break it into 2 integrals. Notice I introduced 2 integrals. At a minus, you may split it again. Also, if you have a constant, you can pull the constant out in front. If you have a constant, you can pull that out in front. Why am I doing this? Well, I want to load up this equation as much as possible. And if you look at it, I now have x to the 4th. X to the n. And it's not -1. I can use this rule. X to the 1st. X to the n. And then we just got to understand, whenever we have a constant, so if we have some constant, don't want to use c, but I'm going to, if I have some constant, dx, it'll always be cx plus k. Where did the derivative of 10 come from? It came from 10x. is what I'm saying. So let's kind of look it out. Let's play it out here. So I'm going to do the antiderivative of x to the fourth. What am I going to do? I'm going to add 1 to the exponent and divide by that number. That's really the rule. Add 1 to the exponent, divide by the number. That's how you anti-differentiate. Plus 18x squared over 2. Again, add 1 to the exponent, divide by that number. Minus 10x plus some constant. So let's check this out slowly to make sure we understand what's going on. The derivative of a constant is 0. No problem. The derivative of 10x is 10. That matches perfectly. Let's take the derivative of this. Well, when you take the derivative of a power, you bring the power down. 2 times the 2 cancels, and we're left with 18x. Awesome. When you take the derivative of this, the 5 comes down and kills the 5. We're left with 3x to the fourth. That's exactly what I have. And so that is my antiderivative function, the original function right there. Can I clean it up a little bit? You can write 3/5 x to the fifth plus 18 over 2 is 9, x squared minus 10x plus k. And that's the simplest as you could have it. Again, just taking the derivatives quickly here, bring the 5 down. 3/5 times 5 is 3, x to the fourth. Nailed it. Bring the 2 down, 18x to the first. Nailed it. Derivative of 10x is 10. If you have a strong derivative background, antiderivatives are not that bad. At least the simple ones, I gotta be careful. But honestly, anyone. If you have a really strong derivative background, you can really just say, let me check it out by taking the derivative and see if it matches. If it matches, you know you did it right. And that's a great thing to know when you're doing a test or any practice exam, is the derivative of this matches there. Awesome. All right, guys. Thank you for watching my first video on derivatives. I hope, not derivatives, on antiderivatives, integrals. All right, so I thank you for watching my first video on antiderivatives, that is integrals. Stay tuned for more.